Welcome to Module 2, the physical characteristics of sound. After completion of this module, you'll be able to explain the physical characteristics of sound and their relationships to each other, and you'll be able to explain how these physical characteristics are interpreted by human experience. Module 2 consists of 2 submodules which describe the 5 physical characteristics of sound. In Module 2a, we'll investigate the 2 most important characteristics of sound, amplitude and frequency. In Module 2b, we'll look at the characteristics of velocity, wavelength, and phase. So let's begin with Module 2a and look at the physical characteristics of amplitude and frequency. As we've said before, sound has physical properties. In fact, it is a physical vibration that exists in an elastic medium. The energy of that initial disturbance is transferred to the surrounding molecules in the medium in which the disturbance occurred, which is usually air. The energy moves out from that point of disturbance throughout the medium where the sound occurred. So we start with an initial vibration, and that energy is transferred to the surrounding molecules and moves through the elastic medium. Well then, what's an elastic medium? By medium here we mean any solid, liquid, or gas that will transmit sound. It must have elasticity, which means that the molecules will return to their original state, just as a stretched elastic band will return to its original state when you let it go. The energy from the sound pushes molecules closer together, compresses them. In doing so, it leaves an area of rarefaction behind where the molecules used to be. Here's a good animation which makes this concept more clear.
Understanding the fundamentals of sound itself is the first step in learning about digital audio and sound. Sound is created by vibrations, such as in a guitar string, vocal cord, or speaker cone. These vibrations disturb the air molecules near them, forcing molecules together, raising the air pressure slightly. The air molecules that are under pressure then push on the air molecules surrounding them, which pushes on the next set of air molecules, and so forth, causing an area of high pressure to move through the air. When these pressure waves reach us, they vibrate the receptors in our ears, and we hear the vibrations as sound. When you see a waveform that represents audio, that waveform represents these pressure waves. The zero line in the waveform is the pressure of air at rest. When the line swings up, it represents higher pressure, and when it swings low, it represents lower pressure. This waveform is the equivalent of the pressure waves in the air below. The amplitude of the waveform is the change in pressure from the peak of the waveform to the trough. A cycle is the amount of time it takes the waveform to go from one amplitude all the way through its amplitude changes until it reaches the same amplitude again. The frequency of the waveform is how many cycles it goes through each second, where 1 Hertz is 1 cycle per second. That is, a waveform at 1,000 Hertz goes through 1,000 cycles every second. A waveform's phase is a measure of how far through a cycle the waveform is. There are 360 degrees in a single cycle, so if you started measuring with 0 degrees at the peak, the waveform would be at 180 degrees at the trough, and back up to 360 degrees at the next peak. The wavelength is the distance, measured in inches or centimeters, between 2 points with the same phase. When 2 or more sound waves meet, their amplitudes add to and subtract from each other. If the peaks and troughs of the 2 waveforms line up, they are said to be in phase. In this situation, each peak adds to the peak in the other waveform, and each trough subtracts from the other troughs, resulting in a waveform that has twice the amplitude of either individual waveform. Sometimes the peaks of one waveform match up with the troughs of the other waveform. The peaks and the troughs will cancel each other out, resulting in no waveform at all. Such waveforms are said to be 180 degrees out of phase. In other cases, the waves are out of phase by some other amount. This will result in a more complicated waveform than either of the original waveforms, as the amplitude at each point along each waveform are added together. Two simple waves can make a complex wave file like this. Continuing to add waves will make a more and more complicated waveform. When you see music, voice, noise, or other complicated sound represented by a waveform, you are actually seeing the result of adding all the waves from each instrument together.
So the energy of this sound wave has physical characteristics. The first one is the amplitude of the sound wave, or its intensity. The second characteristic is the frequency of the sound wave. How fast does it change? What is its rate of change? The third characteristic is the velocity, or how fast does the sound wave move through the medium. Fourth is wavelength. Each sound wave has a physical wavelength, how long it is. And finally, the fifth characteristic, phase, is the timing between different sound waves. In this submodule, Submodule A, we'll investigate amplitude, the intensity of change, and frequency, the rate of change. Let's consider this first one, amplitude. We saw in the last module that amplitude can be compared to loudness, but that loudness is the imprecise and subjective term. Remember? Your grandmother says it's too loud, you say it's not. Amplitude is the objective measure of loudness. Remember when we created the decibel scale in the last section. However, both do refer to the intensity of the sound wave. Amplitude is the measure of the intensity of the sound. When the sound occurs, it will cause a certain amount of compression to the molecules, and the maximum compression is the maximum amplitude of the sound. As the molecules compress, they leave behind an area of rarefaction, which is the minimum amplitude of the sound. What is the softest and loudest sounds a human can hear? Remember from our last module, the range of human hearing for sound intensity is from 0 dB, the threshold of hearing, to 120 dB, the threshold of pain. So our first physical component of a sound wave is amplitude. Next, let's take a look at frequency, the rate of change. Just as amplitude and loudness refer to the same concept, so frequency and pitch refer to the same concept. But there is a difference. Pitch is the imprecise term and subjective term. Frequency is the objective measure of pitch. Again, both refer to how fast the sound wave is changing. Frequency is a number that can be measured. In fact, it's the number of cycles which are completed in 1 second. The unit of measure is the hertz, named after Heinrich Hertz. Just as we have a range of human hearing with amplitude from 0 to 120 decibels, so we have a range of human hearing with frequency, which runs from 20 hertz to 20,000 hertz. That's 20 cycles per second to 20,000 cycles per second. The K in the 20K hertz refers to the prefix kilo, which means 1,000. Heinrich Hertz lived in the last half of the 19th century, and he is accredited with discovering radio waves. It was circa 1960 that they changed the measurement of frequency from cycles per second to hertz, in honor of good old Heinrich. Bye now, Heinrich. To make this more clear, let's consider an example of two different frequencies. Here we see a graphical representation of two different sound waves. From left to right, we'll measure time, which is also another way of measuring frequency, since frequency is a measure of cycles per second. From top to bottom, we'll measure intensity, or amplitude of our sound waves. Notice that the amplitudes of both seem to be approximately the same. However, the frequencies look different. Before we go on, stop and think which frequency is higher, the top one in red or the bottom one in green. Let's see if you got it right. If we look at just this amount of time, we see that in the top waveform, we have 1 complete cycle, whereas in the bottom waveform, we have 2. Therefore, there's more cycles in the bottom for the same amount of time, therefore the frequency is higher. Let's take a listen and you'll notice that the pitch is also higher. So this completes Module 2A, Amplitude and Frequency. But before we continue, I would like you to consider, can you describe the difference between amplitude and loudness? Can you describe the difference between frequency and pitch? Can you describe how frequency is related to amplitude? That is, as one changes, how does the other one change? If so, please continue to Module 2B, where we'll look at velocity, wavelength, and phase.